Hello students, welcome back to the classroom point. In our previous classes, we have completed Raoult's law for liquid in liquid type of solutions and vapor pressure, vaporization and also boiling point. So in our today's class, we are going to discuss the ideal solutions, non-ideal solutions along with azeotropic mixtures also. So let's begin the class. Ideal solutions. So here composition of the liquids can be classified into two categories basically. One is ideal solutions, second one is non-ideal solutions based on the intermolecular attractions between the solute molecules and solvent molecules. And here we are going to discuss all these ideal solutions and non-ideal solutions are liquid in liquid type of the solutions but not in the solid in liquid type of the solutions. So in the liquid in liquid type of the solutions, based on the interaction between the solute and the solvent, how their vapor pressures and boiling points are going to vary. That we shall discuss now. So ideal solutions means, now let us take the two liquids. Liquid A is present in the first beaker and liquid B is present in the second beaker. So in the liquid A, the molecules have some interactions. Some attractions are present. Similarly, in the liquid B, the molecules have some attractions. So if the attractions between the two A molecules is equals to attractions between the two B molecules, so whenever you mix both A and B and get a solution, so we get the solution of A and B. In this solution also, if A molecule and B molecule attractions are similar to that of AA molecules and BB molecules, then such type of solutions are called the ideal solutions. So here, that means here if you need 10 calories of energy to break the attraction, here if you need the 20 calories of energy to break this attraction. So these two are different. Here by adding these two, whatever the molecule you are going to get, so that molecular energy should be the average energy of both of these. In such cases, what happens is no energy absorption takes place, no energy loss shall takes place. So the intermolecular attractions between the like molecules, AA molecules, BB molecules, must be equals to the intermolecular attractions between the unlike molecules, A and B molecules. So such type of solutions are known as the ideal solutions. So what happens if these things happens? So if attractions are similar, so for breaking of the bond and formation of the new bond will not require much difference of energy. That means to break this bond, whatever energy you are providing, the same amount of energy shall be released when these two get attracted each other. That means net amount of energy, net enthalpy change is equals to 0. So for all ideal solutions, delta H mixture of the solutions is equals to 0. And these ideal solutions not only should have the similar interactions, but also should have the similar size and shape. If they have the similar size and shape, then if you take 1 liter of the A liquid and 2 liters of the B liquid, you get, by mixing these two exactly, you get the 3 liters of the AB solution. Why? Because they have the similar size and shape as well as attractions also same. When attractions are same, the distance also shall be same. That is the reason why there shall be no increase in the volume or no decrease in the volume. That means change of the volume is not observed. That's why here we can write down that delta V, change of the volume in the mixture, is equals to 0. Now, the vapor pressures, if you take the vaporization process here, the escaping tendency, here A molecules form the vapor, here B molecules form the vapor. How freely the A molecules and B molecules are forming the vapors, in the same manner, whenever these two are mixed, then also they can form the vapor in the same manner. The reason here is the attraction forces are similar to each other. That is the reason why the escaping tendency of the molecules from liquid to vapor is similar in the case of the solution with their individual liquids. That means here we can write down that escaping tendency of AB molecules is similar to AA molecules and BB molecules. This is escaping tendency. Here delta V mix equals to 0, delta H mixing is also equals to 0. And what about delta S value? Delta S mixing is also always positive. Remember that whenever two liquids are going to form the homogeneous solution, in this sense, the intermolecular attractions here in this case ideal solution is similar and also size also similar. By mixing themselves, it is showing that it is a spontaneous process, and the disturbance always increases. All type of solutions, both ideal solutions as well as the non-ideal solutions. That is the reason why change of entropy of the mixture is always equals to positive, and delta G of the mixture is always equals to negative. The reason is it is a spontaneous process. Then what could be the graph if we see for this one? And remember that all ideal solutions follows the Raoult's law. So in our previous class, we have discussed the Raoult's law. So in that Raoult's law, we have seen that P naught A, here P naught B, mole fraction of A equals to 1, mole fraction of B equals to 1, here mole fraction of A equals B equals to 0, here mole fraction of A equals to 0. The graph comes like this. So here P total is equals to PA plus PB. This is the vapor pressure, and here PB equals to P naught B XB, here PA equals to P naught A XA. So all this we have already discussed in our previous class. So whatever the graph was available or applicable for the Raoult's law for liquid in liquid type of solutions, the same is given by the ideal solutions also. Then what could be the examples for the ideal solutions? Ideal solutions examples are, let us take few examples. N-hexane plus N-heptane. Just only one CH2 difference is there. That's why much difference in size and attractions cannot be observed. That's why it can form the ideal solution. Second one is benzene plus toluene. So again one CH2 difference is there. Third, toluene and xylene. Here also only one CH difference is there. So where similar sizes are present, then such type of the solutions are known as the ideal solutions. Not only that, they should have the similar interactions between the unlike molecules, like AA like molecules also, and unlike molecules must have the similar interaction forces. So this is about the ideal solutions. Now let us discuss about the non-ideal solutions. So non-ideal solutions exactly opposite to the whatever the points we discussed so far about the ideal solutions. So non-ideal solutions should not have similar interactions. So we can write down that do not have same interactions. That means AB interactions are not equals to AA interactions and BB interactions. So either AA interactions are more, or BB interactions are more, or AB interactions are more. That's why the interactions are not equal. Once interactions are not equal, automatically there shall be some loss of energy or there shall be some gain of energy. That's why delta H mixing By mixing the liquid, this value is not equals to 0. It could be positive value or it could be negative value. So when interactions are not same, when enthalpy changes are not same, then automatically when sizes also could not be same, then automatically delta V mixing of the volume is not equals to 0. The reason here is if you add 1 liter of the A and 2 liters of the B, if AB molecules interactions, if these two molecules attractions are stronger, then 1 liter of A and 2 liters of B will give less than 3 liters. Why? Because by adding these two liquids, they get so much attracted so that the volume decreases. If the attractions are not equal, that means if AB attractions which are weaker than the AA attractions and BB attractions, then by mixing the A liquid with the B liquid, since the attractions cannot be formed very freely and easily, automatically they start repelling each other, so that volume gradually increases. That's why delta V mixing is not equals to 0, and it is not following the Raoult's law. When all these parameters are not equal, then it do not obey the Raoult's law. So when it is not obeying the Raoult's law, this type of the graph is not observed for the non-ideal solutions. So let us see how many categories of non-ideal solutions are there. These non-ideal solutions are of two categories. The solutions which are showing positive deviation from the Raoult's law, and the solutions which are showing the negative deviation from the Raoult's law based on the attractions between the AB molecules and AA molecules and BB molecules. So let us see that now. So one side we shall take the non-ideal solutions showing positive deviation from Raoult's law, and the other side we shall take the solutions showing the negative deviation from Raoult's law. So how they are showing the positive deviation and how they are going to show the negative deviation. Again, here also regarding the intermolecular attractions only. So positive deviation is possible if AB interactions are weaker than AA interactions and BB interactions. So how this is possible? Imagine we have taken the AA molecule where some attractions are present, BB molecules, some attractions are present. By mixing this, we got the AB liquid. So here also some attractions shall be developed between the A and B molecules. If these attractions are weaker than AA attractions and BB attraction, then the molecule cannot come close to each other. Then in such cases, what is to be done? So when AB attractions are weaker, that means AA attractions and BB attractions are stronger. If these attractions are stronger, to mix both of these two liquids, we need to provide some amount of energy to the solution to break these stronger attraction forces and to convert that into a solution that is having the weaker intermolecular attractions. So whatever when weak intermolecular attraction is developed, the energy released will be very less. But we are breaking the strong intermolecular attractions and getting the weak intermolecular attractions. To break the strong intermolecular attractions, we need to provide the more energy than what we are going to obtain. So automatically, finally net amount of energy is supplied, not released. That is the reason why here for positive deviation solutions, delta H mixing is equals to positive. Then what about the volume? Since attractions are not so strong, the molecules try to be away from each other so that the volume increases. That is what I said earlier. If 1 liter of A and 2 liters of B is taken, the volume of the final solution could be higher than the 3 liters, not exactly equals to the 3 liters. So that here we can write down that delta V mixing is also equals to positive. And what about delta S value? Delta S value is always positive for all type of solutions, so that we can write down that delta S mixing is positive, and here delta G mixing is the only thermodynamic parameter that is negative. The reason is it is a spontaneous process that is going to mix. Then how it is showing the positive deviation? If we take a graph that is Raoult's law graph, we know that so this type of graph we have taken P naught A, P naught B, XA equals to 1, XB equals to 0. Here XA equals to 0, XB equals to 1. So XB varies. So in this Raoult's law, see here P naught A value is this one. Now when it in the solution, attractions are weaker. When attractions are weaker, automatically the vaporization increase, vapor pressure also increase. This Raoult's law graph is basically about the mole fraction versus the vapor pressure. Since these attraction forces are weaker, automatically whenever they are in the solution, they will show the higher vapor pressure than the Raoult's law graph. So like this, higher vapor pressure. That means according to the Raoult's law, we know that PB equals to P naught B into XB. But this value is higher than this value. So that we can write down that PB is greater than P naught B XB. And similarly here PA value, according to the Raoult's law, PA equals to P naught A XA. But now this value is higher, what it is showing practically. So we can write down that PA is greater than P naught A XA, and this total vapor pressure, whatever we expected equals to PA plus PB, now it is not observed. Why? Because the value is even higher than this expected value. That's why total vapor pressure of the solution is higher than the sum of the partial pressures of the both the liquids PA plus PB. Let us take an example how this is going to take place. So when we take the acetone molecule and alcohol molecule, see ethyl alcohol I am taking like this here. So in ethyl alcohol molecule, hydrogen and oxygen are attracted by the hydrogen bond. So to this solution, if I add acetone molecule, acetone molecule cannot form this much strong hydrogen bond, so that whenever it is acetone molecule is added, it will break these attraction forces and make the molecules free, so that they can easily vaporize and form the more vapor pressure. Hence, they are showing the positive deviation from the Raoult's law. So, this is about the solutions showing positive deviation from the Raoult's law. And one more point here is, in the solutions in which the solutions which are showing the positive deviation, they have the more tendency to escape compared to their original liquids. See here, PA is this value, but experimental value, PA value this much. That means in the solution they have the more escaping tendency than the individual liquids. Now let us see the negative deviation. So negative deviation is possible when intermolecular attractions between the solute and solvent are stronger than the solute-solute and solvent-solvent. That means AB attractions are stronger than the AA attractions and BB attractions. So what happens if attractions are stronger? Let us take this similar example here. See, AA molecules are taken and BB molecules are taken. Now here some attractions are present, but A and B when mixed, these attractions are stronger than the AA attractions or BB attractions. So the molecules come very close to each other. Then how these thermodynamic parameters are going to change? That means we are going to break the weak attractions and going to produce the stronger attraction. To break the weak attractions, we need to provide the less amount of energy. But when strong attraction is formed, more amount of energy shall be released. So that is net amount of energy finally is equals to negative because more amount of energy is going to release. That is the reason why here delta H mixing, enthalpy of the mixture is equals to negative. Since strong attractions are formed, now if you take the 1 liter of A and 2 liters of the B, see here the attractions are stronger, so the molecules come close to each other so that the volume decreases less than 3 liters. So that delta V mixing is equals to negative. And the fourth parameter is, even though the intermolecular attractions are decreases, but delta S mixing is the only parameter that is positive here. The reason here it is spontaneous process. Though the intermolecular attractions are stronger, that doesn't mean that the randomness changes. When you compare the solutions with the ideal solutions, then intermolecular attractions randomness is less. But ultimately final value intermolecular attractions, whenever two different liquids are added, intermolecular attractions may be different, but randomness always increases. So that's why delta S mixing value is equals to positive. Next, since it is a spontaneous process, delta G mixing is equals to negative. So here if you observe, all these are positive values except this value. Here all these are negative values except this value, delta S. Next, how we can compare this formula and this one with that? Here also the solutions are not following the Raoult's law. Do not obey the Raoult's law. Do not obey the Raoult's law. So when they do not obey the Raoult's law, automatically the graph, whatever we expected for the Raoult's law, cannot be followed. This is what rough graph, P naught A, P naught B, XA equals to 1, XB equals to 0, XA equals to 0, XB equals to 1, and XB variation is observed. So every time the attractions become so strong that their escaping tendency gradually decreases. When escaping tendency decreases, automatically evaporation decreases, vapor pressure also decreases. That's why they show the negative deviation. Vapor pressure decrease here also vapor pressure decrease, here also vapor pressure decrease. That means here we can write down that PA value, sixth point, PA value is less than P naught A XA and PB value is less than P naught B XB and P total is less than PA plus PB. So like this, because all are less values. Let us take an example here. When acetone molecule is added to the chloroform, so in chloroform there are 3 chlorine atoms which have the partial negative charges and a hydrogen. That's why they take the electrons from the carbon, so that carbon almost feels more positive charge. To avoid that positive charge, carbon withdraw the electrons from the hydrogen, so that hydrogen gets the partial positive charge and carbon gets the partial negative charge. So here the extent of positive charge whatever is developed is equals to the extent of positive charge developed on the hydrogen. And here oxygen gets partial negative charge, carbon gets partial positive charge. Here some dipolar interactions are formed. This dipolar interaction strength is equals to the hydrogen bond strength. That's why here we can call the hydrogen bond is formed in this case. So when acetone molecule is added to the chloroform molecule, due to the formation of the strong intermolecular attractions, now acetone cannot escape and chloroform also cannot escape. So finally their both escaping tendency decrease. That's why the total vapor pressure gradually decreases. So I hope you understand about the ideal solutions and non-ideal solutions. So we shall meet in the next class. Thank you all.